Hey everyone, so in the previous videos we saw the theory and we also worked out some examples of how to do hierarchical clustering. In this video we are going to see how to implement this on our studio. I will not be providing this PDF along with the video. The intention is that this will make you stop and write the commands in our studio yourself as opposed to copy pasting it. So I believe writing or typing yourself is a more effective way of learning. So yeah, let's start. So this is the data set that we will be working on, downloaded from Canvas. So I can see that there are the dimension of this data is 20 and 4, 20 rows, 4 columns. So 20 people in this data set, or 20 is the sample size and 4 variables. So if I look at the head or the snapshot of the data, this is what it looks like. So we have variable chest, waist, hips, gender. So what we're going to do, so basically our goal is to cluster this data set, to cluster the 20 people based on these variables. Now what we will do is we will put this gender variable aside. We'll pretend that we don't have it. And then we will cluster the 20 people based on the chest, waist, and hip measurement. And then we can see whether we get a group of all males and a group of all containing all the women, basically. Okay, so we'll use this gender to kind of help us make sense of our clustered results if possible. So we remove the last column because we are only clustering based on chest, waist, and hips. So this is the data set. So if you remember, for any clustering method, more than what we need is the distance matrix that will give us the distance between the different people in our data set. So to calculate this distance, we use this function called dist. So it's important to note that this d that we get using this distance function is not actually a matrix. So if I do class of this d, it's an object of class distance. So even though this slide says distance matrix, I put your distance matrix to be consistent with the notation that I used or with the terminology that I used in the previous videos. So anyway, so you use this distance function, I give it my data set, I specify the kind of distance I want to use. So I can swap this for other kinds of distances, but we use Euclidean distance here. So this d, again, even though I say distance matrix, its class is actually of this type distance. Dimension is null, which is okay because this is not a matrix really. So there's a couple of our functions that you can use. I'm sure there's more than the ones I've listed here for implementing this hierarchical clustering. One is the linkage function in package mdendro. So I actually wanted to use this, but it turns out that mdendro package is not compatible with my R version. So I don't want to install different versions and play around with it. So we won't be using this linkage function. hclust is another function. So this is what is used heavily in the textbook as well. So we will use hclust. So how do we use hclust, right? So first we look at single linkage. So I'll use this function hclust. Input is the distance object d. Specify we want to use single linkage, so you write single, you plot CS. So CS, so S is for single linkage. So this is the dendrogram. So I hope you know by now how dendrograms work, right? I've discussed them in my previous videos. So there is one issue that I want to mention before I proceed, and that is of ties. So if let me see, I want to plot this distance. Yes, so this is the distance object that contains distances between all of the elements, and this is the 18th object. Okay, so why 18? So I see that the first now groups to be merged is 16, 15, 12, and 18. So if you remember the algorithm that I discussed in the video, you typically merge 2 clusters at a time, right? But here I'm merging 4 of them. So that's basically because we have ties. So what do I mean by ties? So this is the distance matrix. Not matrix, but I'm just going to call this as matrix anyways. So distance between 18 and this is 15 is 1. Okay, this is 1. So if this was the only one in this matrix, I would merge 18 and 15 first. But as I can see, the distance between 18 and 16 is also 1. Distance between 16 and 15 is, however, 1.4. So this is a different number. And what else do we have here? We also have a 12. So let's look at distance between 18 and 12. So is this last element here 1, right? I have a 12 here. So basically this is a problem of ties, and this is quite a complex issue. It's not easy to break ties. So one thing that we can do is go back to the distance matrix. I look at 18 and I see, okay, 18 and 12 have are one distance apart. 18, 15, 18, 16. I'll just pick any one of these elements randomly. So maybe I'll start by merging 18 and 16 in my first step and then proceed ahead. So anytime there is a tie, I'll just pick one element out of, you know, all the possible candidates. The problem with this is it will give you different clustering structures. So if I pick 16, I'll get a different clustering structure. If I merge 18 and 15 instead, I could get a different structure altogether. So it's not a very robust mechanism. So I tried to see what mechanism HClust uses to deal with this problem of ties, and the answer is I don't know. I wasn't able to see. However, for this linkage function, I think I probably have a reference here. Yes. So for the linkage function, right, it uses this variable group approach. What is this approach? I'm not going to discuss it, but there is this reference paper here. Now, I don't expect you guys to actually read the reference paper, but the point I'm trying to make here is it gets quite complicated. There are methods. When I tried to see different ways to break ties, a bunch of research papers popped up. So I know what linkage does. I don't know what HClust does yet. If I find out, I will let you all know. It's not a super important problem right now. We're not going to think about ties so much, but it's just a good idea to be aware of this problem about ties, okay? So I'm not going to talk about ties any further, but you guys should always look for ties and see how they are being dealt with. So next we look at complete linkage. So again, HClust function, D, I say method is equal to complete. This is the dendrogram. So here R is doing something slightly different. It merges 12 and 18 first, and then it merges them with 15 and 16. So yeah, so this is the complete linkage. For average linkage, I just specify method equal to average. I plot and I get this dendrogram. So this important problem of how many clusters, okay? So I mentioned the elbow method, so we will definitely look at this elbow method, and we have extra information, right? So there was this column on gender that I did not consider. So I know that this data has measurements on men and women, so basically 2 groups. So what we can do is we can use this information to select our cutoff so that we get only 2 clusters, right? So for single linkage, right, what I want is I want to basically get 2 clusters in my output. So let's see, where do I have 2 clusters? So if I decide my cutoff, right, so if my cutoff is over 4, so at 4 I can see that all of my groups are all of my elements are in a single group. If my cutoff maybe not even 4, probably more, this, I don't know if this is maybe 4.3, 4.5. So if my cutoff is somewhere up here, larger than, you know, above this line, then I'm going to have a single final group. If my cutoff is, say, somewhere here, right? So then I have this one group, and then I have this another group. It has only one element, but I have two groups. So if I'm looking for two groups, this is one group and this is my second group, okay? So let's see. So how do I extract this from this CS? So I have this function called cut tree. So I do cut tree CS because I'm looking at the single linkage output right now. H is equal to 4. So cut my tree at height is equal to 4. Height is equal to 4 is somewhere here. I know that this should give me two groups. So I stored this output in in LAB or for label, and I output here. So this is what I get. The first element is in group 1. All of the other elements are in group 2. Okay. Let's see. So I have this. So this title says PCA for single linkage. So another thing that we'll do here, so I haven't seen people use this method a whole lot, but this is done in the textbook. So if you want more information or if you want to understand this further, check out your textbook. So what I have is we're doing here principal component on this distance matrix. Okay, so we are saying that our distances is our data, and we are trying to see what is the underlying dimension in of this D. So let's see, let me go down. Yeah, so I have this print comp which I've implemented on my distance data or the distance matrix, and what I've done is I plotted the first two PC scores. Why two? Because I can, plot the first two elements. So I have these first two PC scores. So this is the data set, and I'm also labeling these points. Okay, so the labels are coming from this cut tree function that I showed you right now. So let's just see here. So yeah, we can visualize this better. So we can see that our distances, right? Because we did PR comp on the distance data. So our distances from two groups, right? I can see that I have a bunch of points here. We have a bunch of points here. But the output from this single linkage is not in sync with this. So what is a single linkage saying? That all of these twos, all of this is a single group, and this one is in its own group. Ideally, what we would want is we would want all of these elements to be in a group, and maybe all of these elements to be in their own group. So we can see that single linkage is not doing very well, right? So distances, so the first two principal components of distances give me a group here and a group here. Right, I'm simply saying that because I see a bunch of items are here and a bunch of items are on this side of my graph, right? So I can see two groups, but single linkage is saying that all of this is in group 2. Okay, so maybe single linkage isn't doing very well. So let's look at complete linkage. So again, this is the dendrogram. Again, I want a cutoff which will give me two groups, right? So yeah, so I can pick basically anywhere here. Okay, anywhere from probably about 10 or so, anywhere from 10 to 10, 11, 12 or something should work. So basically if my cutoff is in this region, then I have this one group here and this other group here, right? I want a cutoff so that I get two groups. So again, I'm saying cut tree for complete linkage. So I have CC and cut it at height 12. So 12 is somewhere here. I think even if I give it a 10, it will still do the same thing. Okay. And these are the labels. And what does it say? First element is in group 1. Second, third, fourth are in group 2. Fifth is in group 1 and so on. So this is a different grouping structure. Okay. So again, I have this PC, which has the principal component of the distance, of the distances. And I plotted this. Okay, so what do I see? So again, I'm plotting the first two scores. I'll go to the next slide. You can see it better. So this is first component versus the second component, and the labels are from the hierarchical algorithm, or labels come from output of this. Okay, these are the labels that I'm using. So I can see now that, okay, so my my principal components say that this is a group and this is another group, and so all of these are labeled as ones. So complete linkage is saying that this entire data, let me see if I can maybe highlight it with a pen, that, nope. Yeah, well, this is not working right now. But anyway, so what I'm trying to say is that all of these points are in a single group. All of these twos are in a single group. So this is much better than the results for single linkage. Okay, this is not perfect still, but it's not bad. Average linkage, again, we want to get two groups. So let's see, cutoff is 7.5. So we want the cutoff to be above this line, right? So this is probably between 7 and 8, so 7.5. So the cutoff is somewhere in this range, then I have this one group and I have this one group, right? So two groups. So again, if you look at this, do the principal components and look at this graph, you see that all of these points are in one group and all of these points are labeled to be in another group. So probably this is slightly better than complete linkage, right? Because in complete linkage, what did we have? This one was, this point was in group 1, and in average linkage, this point is in second group. So we look at the elbow method. So elbow method is something I would use because frankly it makes more sense to me. So you will need to install this library called Facto Extra and also nbclust. So this is basically, this function will calculate this number of clusters. So you give in your data, hcut. So this function hcut basically means I want to do hierarchical clustering. So there are different other kinds of clustering methods. We'll see k-means next week. So hclust basically implies hierarchical clustering, and this wss means we want within sum of squares. So go ahead and Google this option. You'll see what are the different possible values that you can input here. So I plot this m, and this is the result that I get. Okay, so as I increase this number of clusters, total within sum of squares drops. So I don't know. So again, so we have to decide which is the elbow point. Is it 2? Maybe. Is it 3? Maybe. It could be 4 as well. I would probably pick somewhere between 2 and 3 because these seem to have a larger drops. So what I mean to say is 2 is followed by a larger drop, 3 is followed by a larger drop than these other points. I would pick somewhere in between here. Again, this is a quite subjective. It's possible different people pick different numbers. So I'm always a fan of or a proponent of writing my own code. So I found this function online. I don't always trust all the functions, so I would write it myself actually. But if you guys are interested in writing your own function to generate this elbow method, let me know. I'm more than glad to help you. Okay, so I'm not putting this here because I'm sure all of you are already struggling with this new online system that we have now. So I don't want to burden you with additional things. So this function exists, so it's not super important that we build one ourselves. But I have a few questions about this. So for hierarchical clustering, I am not sure which method it picks. We know that there's the single, complete, and average linkage. I'm not exactly sure which one it uses. Okay, so maybe if you find out, you can let me know. So the best way to avoid any questions is to construct the function yourself. So I'll be more than happy to help you in case you want to venture in this direction. Uh, Anyways, I think that is all for this week. Maybe next week we can try and build this elbow or a function to generate this plot. Anyway, so there's been a lot of videos for this week, so I will stop here.